Okay, everyone, welcome back to the last video on the lecture material for the first week. This time we will finally dive into the true power of panel data models, namely that we will finally introduce individual heterogeneity in our models. So let's jump directly into the material. So here we are. We have now panel data models with individual heterogeneity. We finally start exploiting the fact that we have seen the same individuals over several time periods, and that every time we actually observe also the same variables. So before, as we discussed before, we have basically treated the panel as a system of equations and completely disregarded the fact that it's always the same individual in several time periods and the same variables. So our model still looks pretty much the same as before. So here we have it. Now the only change is that this VIT is actually, it has an error components form. So this model is now called an error components model, because the model error can be divided into two parts. So one is the individual heterogeneity part, the alpha I, and we have an idiosyncratic error part. So this is pretty much, it's also the same notation as we used before. This is the UIT that we think is kind of like a random noise, hopefully, right? So that there's no error, no variables in there that we are neglecting so far. Okay, of course, both things are unobserved, and like alpha I has this special property that it's time invariant. So this is what we mean with unobserved individual heterogeneity, which is time invariant. So you see, that's why it doesn't have a T index. Now, why is alpha I so important? Well, as we discussed in the very beginning, we interpret that this alpha I captures time invariant individual specific characteristics that may be correlated with observed characteristics. So for instance, we can think of like individual ability, the motivation, genetics, management quality, whatever. Um, the only condition that, of course, we need is that these variables are credible to be time invariant, at least in the short run of the panel length that you have. Okay, now recall that we have short panels. So we have a large N, we have a large number of individuals, but we have only, let's say, 5 time periods. And because that asymptotic setting doesn't change, there's absolutely no way in which we can consistently estimate the alpha I, because for each alpha I, we only have T data points. So no chance there. However, that's not necessarily bad news, because we're not necessarily interested in the effect of alpha I itself, because often it's not even clear in what unit motivation or genetics can be measured in. So why alpha I is important is that it may be correlated with observed variables for which we do want to know the effect. And if we do not take into account the alphas, then we end up with an omitted variable bias, and well, that's bad, obviously, right? And therefore, now that we have panel data, we can actually alleviate, we can reduce the chance of omitted variable bias by actually taking those unobserved individual characteristics into account. Okay, now alpha I is not observed. That's a problem. So typically we will have to impose additional assumptions in order to account for the presence of this alpha I. A very simple assumption is the random effects. So the random effects assumption or random effects approach, you simply assume away the problem. You say the alpha I is there, but it's not correlated with the observed explanatory variables. And well, of course, then you can simply put the alpha I back into the error term, the VIT, like the composite error term. This thing will still be uncorrelated with the axis, and you get a consistent estimator pretty easily. However, now that you know that the VIT has this structure with the alpha I, you have some more information about the variance, and therefore you may be able to improve upon the standard pooled OLS estimator using this random effects estimator. However, in many cases, like this uncorrelatedness assumption is not credible. So therefore, in practice, people typically prefer the fixed effects approach, in which we make absolutely no assumptions whatsoever upon the relationship between the axis and the alpha. Okay, now how do we deal with the presence of fixed effects? Again, we don't want to impose any assumptions on the alpha. So this is our original model. Yeah, now written kind of that we see that the alpha I is explicitly there. And of course, we can use a simple idea. Well, we know that the effect of alpha, yeah, so it's additively added here in each time period and it's time invariant. So the effect of alpha on yi1 will be the same as the effect of alpha on yi2, right? So if I take the difference between yi2 and yi1, the alpha will actually drop out. So you see that we use this delta notation here. The deltas simply mean that you take the yit, for instance, for delta yit, and you subtract the data from the previous period. And if you do that, well, the alpha I drops out because it doesn't depend on time. Unfortunately, what you see here is that now, because we have this differencing, we kind of lose one time period. Because like in delta yi1, we would have the, yi0, and yi0 is not observed. So we can only start at yi2 here. Now, this transformation that we used with this delta, that is called first differencing or just differencing. Well, no, the good part is that, well, the unobserved effect drops out. The bad part is that we lose one time period and we have to check our assumptions, right? So if we were kind of to take model 24 and apply pooled OLS on the difference data, we would require that this delta x is orthogonal, meaning uncorrelated with the delta u. Okay, let's see, does that work? Yeah, well, I mean, this is pretty much delta x, this is delta u, so let's open the brackets. We see these terms here, and I marked these terms here in red. Those are terms where we have x combined with u, and both are from different time periods. And therefore, our previous assumption that we had for consistency, like contemporaneous uncorrelatedness, this out of a sudden is not strong enough anymore, right? So because under contemporaneous uncorrelatedness, these terms here are not zero. Okay, so we need to strengthen our assumption. So let's go big. Let's assume strict exogeneity, where now we put the alpha also in the conditioning set. Under this assumption, uh, all these terms here are zero. Yeah? So that's very convenient. So because we have all these terms equal to zero, we get that, of course, also the delta xit will be orthogonal to delta uit. And these are moment conditions that we can then exploit by GMM. In fact, strict exogeneity implies many more moment conditions, but typically we want to exploit those. Like, there's it's kind of our analog to contemporaneous uncorrelatedness on the difference data. Okay, now remark, why do we put the alpha I in the conditioning set? Okay, sorry. Well, we first do something, one more before the remark. These moment conditions you have for each t, right? So you can again pool them together. So by taking the sum across t. And by the way, here and again, never mistake, this should be a 2. So I will change that right away. Okay, if you pull them together, then the dimension of this thing here is of course the same as the dimension of x, meaning k. And therefore you have k moment conditions for k parameters to estimate. And therefore when you use GMM, the beta is just identified and GMM coincides with pooled OLS on the difference data. And this thing here, OLS on the difference data, is known as the first differencing estimator. Okay. Now, I mentioned already that we condition on the alpha I when we talk about strict exogeneity. That's maybe a little bit surprising to you because we talk about fixed effects, and fixed effect sounds a bit like it's a parameter. It's something that is non-random. However, in economics, we simply treat it as another random variable that is drawn together with the observed axis from a large population. Yeah, so it is the same as one of the XITs. The only difference is that, well, it is time invariant, and unfortunately, we cannot see it. Okay, now a warning in that respect. If you happen to Google stuff, if you happen to Google fixed and random effects, you may find websites that explain things very differently. And the reason is that, unfortunately, in the statistical literature, fixed effects and random effects are something very different from the econometrics literature. Yeah? So in the original statistics literature, the fixed effect is really fixed. It's a constant. For us, not. It's a random variable, always. Okay, so a couple of downsides that we already mentioned. We lose one time periods with first differencing, and something that is a little bit more subtle. We can actually not identify effects, we cannot identify betas that are related to time invariant observed characteristics. Because once an observed characteristics is time invariant and you take first differencing, they're wiped out. Yeah, so for instance, like a classic is a gender dummy. So if your gender doesn't change in the next 5 years, then of course, once you take the difference, on top of the fixed effect, also the variable gender will drop out of the model. It cannot be identified. And another downside is that this differencing may introduce negative serial correlation in the difference model errors, because this UIT minus 1 is of course in delta UIT, and it's also in delta UIT minus 1. So there is a clearly negative serial correlation there. Okay, did I forget anything? Let's see. First differencing is one way of removing the alpha from the model. However, there's another one that is very popular. So here we define this bar notation. So whenever we put a bar on top of a letter, that means that we simply take the stratum average, meaning the time series average for each of those variables. And we can then apply the within transformation. So we use this dot notation, y dot dot is simply yit minus the time series average of y. Yeah, and again, because the alpha I does not depend on time, the average, the time series average of the alpha i's is will alpha I, right? So if you take yit minus the average of the y, alpha I will drop out. And after the within transformation, you get this model. Yeah, so it looks pretty much as our original model, just that now every variable has 2 dots on it. Yeah, and there's no fixed effect. And again, strict exogeneity is a really strong assumption. If you think back at the very beginning of the lecture, we talked about strict exogeneity already, and we said that, for instance, it rules out feedback, right? So kind of if current shocks on production affect your future inputs of labor and capital, that would be an example where strict exogeneity cannot hold. We will also see that strict exogeneity is actually too strong for dynamic models, but okay, that comes in the next week. Good, back to the within transformed model. No fixed effect in model 27. So intuitively, we kind of evaluate every variable relative to the within stratum, meaning within group, meaning within individual mean. And strict exogeneity is super strong. It implies that this x dot dot is orthogonal to u dot dot, and this for every t. Again, people like to pool together the moment conditions, probably in order to avoid any j-test. Yeah? Okay, we pool them together. So dimension of the moment conditions is k, where k is the number of time varying covariates. So again, beta is just identified, and this beta hat Fe is called the fixed effects estimator. So when people refer to the fixed effects estimator, they normally don't refer to the first difference estimator, but rather to this estimator where everything is related to the time averages. Okay, that's it. This looks pretty much like least squares. Simply put dots on everything. Yeah, so very simple. Now, in comparison with the first differencing approach, it kind of looks like we are not losing any time periods here, right? So we kind of can start from period 1, whereas before here, where did we have it? We had to start from period 2 because yi0 is not observed. So this may look like, sorry, where are we? Here. This may look like to you that if t is equal to 2, we can actually over-identify beta with the within transformation, but it can only be exactly identified with first differencing, right? So let's go like through this a bit slower, right? So when you have first differencing with t equal to 2, you have exactly one of these moment conditions. So because, well, that's the only thing there is. Um, if you use the within transformation, you have this type of moment condition both for t equal to 1 and for t equal to 2. So you could think, well, I can actually over-identify beta. This is not true. And in fact, if you look at the case where t is 2, both estimators coincide. And this is a nice exercise. Well, clearly, this is why it's on the exercise sheet. Now, the intuition is that similar to degrees of freedom, we kind of fix the stratum average. So on top of the average, there's only t minus 1 informative data points, right? So when I kind of look at, for instance, the sample variance, once I fix the average, I can only move t minus, when I give you t minus 1 data points, I know, if I also know the average, what the tth data point will be. So the last one is not informative anymore. Good. This is a little bit of an outlook. So if strict exogeneity is true, both estimators will be consistent. Now, the fixed effects estimator tends to be a little bit better in terms of like efficiency, meaning lower variance, when there is no serial correlation in the UIT. And first differencing seems to be a little bit better when UIT is a random walk. And you should always kind of calculate both because like if you use software, it's super easy. And if they are very, very far away from each other, that may actually be an indication of a violation of the orthogonality conditions. Nowadays, there are explicit tests for that, but I think they're a little bit beyond the scope of this lecture. Yeah, but just intuitively, if you compute them both and they're very different, something's wrong. Oh, yeah. So we are already at the end. So that was a very quick and dirty introduction to fixed effects methods. We will dive deeper into these issues in week 2. Okay, I hope you found this material easy to grasp. I hope otherwise, again, as usual, let me know. See you.